A speck of dust in your home holds a secret older than the sun. This is cosmic dust, the universe's fundamental building block, and its journey is our origin story. By the end, you will understand how the atoms in your hands were forged in stellar explosions and sculpted into planets. How did microscopic grains survive the chaos of a supernova to become the foundation of a world like Earth? And what hidden messages do they carry about our deepest past? What does it mean to know that you are, quite literally, made of stardust? The violent death of a star is the universe's ultimate act of creation. This is where our journey truly begins, within the unimaginable fury of a supernova. A star, having spent millions of years fusing hydrogen into helium in its core, begins to run out of fuel. The delicate balance between the outward push of nuclear fusion and the inward crush of gravity suddenly shatters. In a final, desperate surge, the star's core collapses in a fraction of a second, then rebounds in a shockwave of pure energy that rips the entire star apart. For a brief moment, this single event can outshine every star in its galaxy. But this is not just a spectacle of light, it is a cosmic crucible. Within that expanding fireball, temperatures soar to billions of degrees and pressures become so intense that atomic nuclei are smashed together, forging elements far heavier than anything the star made during its life. Atoms of carbon, oxygen, neon, silicon, and iron are born in this instant. The very iron in your blood, the calcium in your bones, the silicon in the sand on a beach, all were created in such a cataclysmic event. Yet these are just free-floating atoms, a chaotic elemental soup. For them to become something more, they must find a way to come together. As the supernova's shockwave blasts outward, it collides with the cooler, thinner gas of interstellar space. This collision is like a sudden, violent chill. The temperature plummets. In that rapid cooling, the newly minted atoms no longer have the energy to stay apart. They begin to stick to one another, nucleating around microscopic seeds. Silicon atoms link with oxygen to form tiny motes of silicate minerals. Carbon atoms bond into specks of graphite or diamond. Flecks of solid iron and other metals condense. In the aftermath of the most destructive event imaginable, the first solid particles in the universe are born. This is stellar alchemy, transforming the energy of a star's final breath into the tangible seeds of future worlds. These microscopic grains, this first generation of cosmic dust, are now cast adrift, carrying within them the elemental legacy of a star that no longer exists. But their journey is only beginning. How could something so small and fragile possibly survive the harshness of space to build something as vast as a planet? While supernovas forge the heavy elements, a quieter, more graceful process spreads the seeds of future chemistry across the cosmos. Consider a star like our own sun, nearing the end of its long, stable life. It does not explode. Instead, it swells into a magnificent red giant, its outer layers becoming tenuous and cool. Over thousands of years, these layers gently peel away, not in a violent blast, but in a sustained, serene wind of gas. This expelled material forms one of the most beautiful sights in the universe, a planetary nebula, a glowing, multicolored cloud of gas that surrounds the fading stellar core like a cosmic flower. Within these vast, luminous clouds, the environment is surprisingly ideal for creation. The temperatures in these drifting outer layers are far cooler than a supernova's heart, yet still warm enough for atoms to move and interact. Here, in the relative calm, something remarkable happens. Atoms of carbon, oxygen, and silicon, forged earlier in the star's life, begin to bump into one another. They stick, forming tiny molecular clusters. These clusters act as seeds, gathering more and more atoms, slowly growing into solid grains of dust. This gentle process, called nucleation, is like frost forming on a window pane, a gradual accumulation from a misty environment. The dust born here is different. It tends to be rich in carbon, the fundamental element of life, and can form into complex, almost fluffy structures. These grains are not just specks of mineral, they are intricate, microscopic architectures that carry within them a more complex chemical potential. As the stellar winds continue to flow, they carry this newly formed dust outwards, enriching the surrounding space with a rich diversity of materials. This is the universe's patient craftsmanship, a slow exhalation that fills the interstellar medium with the building blocks for organic molecules and the potential for chemistry far more intricate than simple rock. So the cosmos employs both the hammer and the brush, both the violent forge and the gentle breeze, to manufacture the raw ingredients of worlds. But these precious grains now face their greatest challenge, a journey across the unimaginable emptiness between the stars. The dust is now cast into an ocean of near nothingness. This is the interstellar medium, the space between the stars. To call it empty would be a profound mistake. Think of it instead as a vast, ghostly sea, a fog so thin its density is 1,000,000 trillion times less than the air you breathe. If you could float here, you would see a faint, pervasive glow, the combined light of distant stars filtered through a haze of microscopic particles. Within this ethereal realm, our dust grains are not merely drifting, they are working. Each tiny speck acts as a shield, absorbing the harsh ultraviolet radiation from nearby stars. This protects fragile molecules floating nearby and causes the grain itself to warm up, glowing with a gentle infrared heat that telescopes can detect. It is this faint warmth that allows us to map the hidden anatomy of our galaxy, seeing the dark clouds where new stars are cradled, but perhaps their most vital role is as a meeting place. The surface of a dust grain is a cosmic crossroads. Atoms and simple molecules drifting through the void, like hydrogen and oxygen, are far more likely to stick and react when they meet on this solid anchor. A water molecule might form here, or carbon monoxide. These grains become the universe's first chemistry sets, tiny laboratories where the basic ingredients for life begin to assemble in the darkness. For millions of years, our dust travels through this silent, diffuse sea, gathering molecules and occasionally colliding with other grains, sometimes sticking together to form larger, fluffier aggregates. They are preparing, though they do not know it, for a much more dramatic change. All this quiet chemistry is merely the prelude, the calm before a gravitational storm gathers them in. Gravity is the quiet architect waiting in the wings. Across immense stretches of time, its subtle pull begins to gather the diffuse material of the interstellar medium. Like mist condensing into droplets on a cold morning, atoms and dust grains are drawn together, coalescing into vast, dark structures that blot out the light of the stars behind them. These are molecular clouds, the shadowy wombs of future solar systems. They are profoundly cold, only a few degrees above absolute zero, and so dense that a single cloud can contain the mass of 1,000,000 suns. Within their murky depths, the journey of our cosmic dust takes its most decisive turn. This environment is a world apart from the thin sea of interstellar space. Here, the dust grains are no longer lonely travelers. They are packed together in a thick, frigid fog. As they drift, they become coated in layers of frozen water, carbon monoxide, methane, and ammonia, gathering icy mantles that make them stickier and more complex. But the true catalyst for change comes from outside. A shock wave ripples through the cloud, perhaps the distant echo of a supernova or the powerful stellar wind from a newborn giant star nearby. This wave of pressure acts like a cosmic snowplow, sweeping through the cloud and compressing vast regions of gas and dust into even denser knots. within these compressed pockets, something magical happens. The dust grains, now cushioned by their icy shells, begin to bump into one another. In the cold, dense environment, these collisions are gentle, occurring at walking speed. They do not shatter. Instead, they stick, held together by weak molecular forces and the frosty glue of their mantles. This is the process of coagulation, a slow, persistent gathering. Two grains become one slightly larger, fluffy cluster. That cluster collides with another and another, growing not into a solid rock, but into a fragile, fractal web of material, like a microscopic snowflake of cosmic proportions. These are the first planetesimals, the primordial seeds from which planets will grow. As physicist Carl Sagan once reflected, the nitrogen in our DNA, the calcium in our teeth, the iron in our blood were all forged in the interiors of collapsing stars. Here, in the deep freeze of a molecular cloud, that stardust finally begins to clump together, taking the first tangible step toward becoming a world. It is a shocking aggregation, transforming a fine mist of microscopic particles into the foundational blocks of a solar system. But how does this delicate, fluffy snowball evolve into the solid, round planet beneath our feet? The delicate snowflakes of stardust are about to enter a cosmic whirlpool. As the central knot of the molecular cloud collapses, igniting a new star, the remaining material does not simply fall into the fiery newborn. Instead, it obeys a fundamental law of the universe, conservation of angular momentum. All that slight, inherited spin from the cloud's gentle rotation becomes amplified as it collapses, forcing the infalling gas and dust into a vast, flat, spinning disk that encircles the young star like a celestial carousel. This is the protoplanetary disk, a swirling construction zone where planets are literally under assembly. Within this churning maelstrom, our dust grains face a new and dynamic existence. They are no longer drifting in a quiet, cold fog. They are caught in a torrent, whirling at incredible speeds within a thin plane of gas. Here, the process of growth accelerates dramatically. Turbulence within the disk acts like a cosmic blender, constantly stirring the material and forcing particles to collide. But these collisions are no longer the gentle, icy mergers of the dark cloud. Now, when two fluffy dust aggregates smash together, they can stick, shatter, or bounce apart, a chaotic dance dictated by their size, speed, and composition. Yet, a powerful organizing principle emerges from this chaos: distance from the star. Close to the newborn sun's intense heat, temperatures are far too high for volatile ices to survive. Only the most refractory materials, the rocky and metallic dust grains forged in stellar furnaces, can persist here. This hot, inner zone becomes a construction site for dense, rocky worlds. Farther out, beyond what astronomers call the frost line, temperatures drop sufficiently for water, methane, and ammonia to freeze solid onto the dust grains. Here, particles grow faster, accreting thick, icy mantles, and the available material is vastly more abundant. This cold, outer region is destined to become the realm of the gas and ice giants, planets with massive cores that can then capture enormous atmospheres of hydrogen and helium from the disk. But for the dust itself, the journey is perilous. Drag from the surrounding gas causes smaller particles to slowly spiral inward toward the star, a journey that could end in fiery destruction. To survive and become a planet, a dust grain must grow quickly enough, through countless collisions and mergers, to become large enough that gas drag can no longer steer its fate. It must graduate from being a passive passenger in the disk's flow to becoming a sovereign body, clearing its own path through the whirlpool. This rapid inward spiral is known as the meter-sized barrier, and for a long time it was a profound puzzle in planetary science. How could a growing ball of dust and ice ever survive long enough to become a planet if the very act of growing to the size of a boulder doomed it to a fiery end? Nature, it seems, found a loophole. The key lies not in fighting the turbulence, but in using it, Within the dense mid-plane of the disk, where the dust has settled like sediment in a river, the gas itself can become unstable. As dust particles concentrate, they can drag the surrounding gas with them, creating pockets of higher density. These pockets, in turn, exert a stronger gravitational pull on the nearby dust, drawing in even more material. This creates a positive feedback loop, a gravitational instability that can rapidly gather vast amounts of material in a cosmic blink. One moment, there is a swirling cloud of pebbles and boulders. The next, through the collective pull of their own combined mass, they collapse directly into a solid object tens or even hundreds of kilometers across. It is a leap of staggering scale, bypassing the dangerous middle ground entirely. Another possibility involves the sticky properties of the dust itself, especially in the colder, outer disk where grains are coated in thick mantles of water ice and other frosts. These icy surfaces are not just cold, they are tacky. When two such fluffy, frost-covered aggregates collide at the right speed, they do not bounce or shatter. They merge like two snowballs smacking together in a perfect pack. This stickiness allows for rapid, runaway growth, clumping meter-sized objects into ever larger assemblies with startling efficiency. Through one or both of these cosmic shortcuts, the barrier is shattered. The result is a planetesimal. This is the turning point. A planetesimal is no longer just a clump of dust. It is a minor world in its own right, a gravitational entity. Its own self-gravity, however modest, pulls it into a roughly spherical shape. It has enough mass to clear its immediate orbit of smaller debris, and its interactions are now governed by the silent, persistent laws of orbital mechanics, not just random collisions or gas drag. The dust, forged in stellar furnaces and assembled in the icy dark, has finally achieved a form of permanence. It has become a celestial body. But this is not the end of the journey. It is the beginning of a new and even more violent chapter. How do these hundreds of planetesimals, all sharing similar orbits around a young star, avoid constant chaos and instead build the orderly planets we see today? The chaotic whirlpool of the protoplanetary disk has given way to a new, more orderly regime. Now the story is no longer about dust, but about worlds in miniature. Billions of planetesimals, each a kilometer-scale sphere of rock and ice, now share the space around the young star. They are no longer passive passengers. Each one, through the simple fact of its own mass, exerts a tiny gravitational whisper on its neighbors. Over thousands of years, these whispers add up. A slight tug here, a gentle nudge there, slowly but inexorably sculpting the traffic of this early solar system. This is the era of gravitational sculpting, a slow-motion ballet where the dancers are constantly, gently changing each other's paths. The result is inevitable. Orbits that were once neatly separated begin to cross. When two planetesimals find themselves on a collision course, the outcome is often surprisingly gentle. Given their relatively modest sizes and the vast emptiness they travel through, their closing speed is frequently slow, a leisurely cosmic convergence rather than a violent smash. When they meet, their own mutual gravity takes over, pulling them together in a final, soft embrace. They do not shatter, they merge to become one, a larger, more massive body. This process, known as accretion, is the primary engine of planetary growth at this stage. A planetesimal might absorb dozens, then hundreds, then thousands of its siblings, snowballing in size through a relentless, peaceful consumption. These growing bodies graduate to a new title, planetary embryos or protoplanets. Some will grow to the size of our moon, others to the scale of Mars. They are no longer just survivors of the disk. They are the dominant gravitational players in their local neighborhoods, clearing their orbits of smaller debris and beginning to dictate the gravitational rules of the system. It is a stately, monumental process unfolding over millions of years. the destiny of a single speck of supernova dust is now irrevocably tied to the fate of a sphere of rock hundreds of kilometers across, a world in waiting. But this peaceful era of accumulation cannot last forever. As these embryos grow, their gravitational influence becomes stronger, their appetites larger, and their paths more dangerously intertwined. What happens when this slow dance of gentle mergers gives way to a far more dramatic and decisive showdown? A single invisible boundary in the swirling disk decides the fate of worlds. This is the frost line, a frontier not marked by any physical barrier but by temperature alone. Its location is dictated by the heat of the young star at the center. Inside this line, the relentless stellar radiation is too intense. Any water, ammonia, or methane that drifts into this inner zone cannot condense. These volatile compounds remain as gases, blown outward by the stellar wind or spiraling in toward the star itself. Only the toughest materials can endure here, the dust grains of rock and metal forged in stellar furnaces. This leaves the inner disk relatively starved of solid building blocks, a construction site with a limited supply of bricks. The planets that form here, like Mercury, Venus, Earth, and Mars, are necessarily dense, rocky, and compact, built from the durable leftovers of stellar explosions. They are worlds of stone and iron. Step across that invisible thermal boundary, however, and everything changes. Beyond the frost line, temperatures plummet. Here, water vapor freezes directly into solid ice crystals. Methane and ammonia frost over. These ices coat every dust grain, not just as a decorative rime, but as a transformative agent. First, they act as a powerful cosmic glue. When two icy grains collide, they are far more likely to stick together than their dry, rocky cousins inward. This stickiness supercharges the process of coagulation, allowing planetesimals to form faster and grow larger with astonishing efficiency. Second, and more crucially, ice is abundant. For every atom of silicon or iron, there are many more atoms of hydrogen and oxygen waiting to become water. Beyond the frost line, the amount of solid material available for planet building increases by a factor of 10 or even 100. It is like moving from a sparse gravel pit to a vast quarry of snow and ice. This abundance is the secret to the gas giants. A core can grow rapidly here, snowballing through the plentiful icy material until it reaches a critical mass, perhaps 10 times that of Earth. Once it achieves this threshold, its gravity becomes powerful enough to perform a feat impossible in the hot inner disk. It can begin to capture and hold onto the lightest elements of all, the hydrogen and helium gas that makes up the vast majority of the protoplanetary disk. This is the birth of a planet like Jupiter, a process that begins with a single water molecule freezing onto a speck of dust in the cold dark. The frost line, therefore, is the master architect of solar system architecture. It creates a natural division, an inner kingdom of rock and an outer empire of ice and gas. The journey of a single volatile compound, dictated by nothing more than temperature and distance, sets in motion a chain of events that determines whether a world will be a barren rock, a watery globe, or a colossal giant. But what about our own world, Earth, which formed inside the frost line? If water could not condense here, how did our blue planet, covered in oceans, come to be? The answer lies in a later, violent delivery from the icy realm beyond. The slow, stately dance of planetary growth was always destined to descend into chaos. As those embryonic worlds grew larger, their gravitational reach extended, transforming gentle nudges into powerful shoves. Orbits that had been stable for millions of years began to warp and cross in unpredictable ways. The result was a period of unimaginable violence, a final, frenzied construction phase where the solar system became a cosmic shooting gallery. In our own system, we see the scars of this epoch etched onto every ancient surface, a chapter astronomers call the Late Heavy Bombardment. This was not a gentle rain of pebbles. This was an onslaught of planetesimals and other planetary embryos, some the size of our moon or even Mars, hurtling on collision courses. The energy released in a single one of these impacts is almost beyond comprehension. When a body hundreds of miles across strikes a planet at tens of thousands of miles per hour, it is not a simple crash. It is a transformative cataclysm. The impactor is utterly vaporized in an instant. The target world's crust is not just cracked, it is melted, excavated, and flung into space. Vast basins hundreds of miles wide are gouged out in moments, while towering rings of molten rock solidify into mountain ranges. The heat from such an event can melt the entire surface of a planet, resetting its geological clock and sterilizing any fragile beginnings. For our long-traveled speck of cosmic dust, now embedded deep within the rocky mantle of a young Earth, this period was a moment of profound existential change. It could have been buried even deeper, driven toward the planet's searing core by the churning mantle. Or, in a more dramatic turn, it could have been part of the surface material that was violently blasted back into the void, liberated from its new planetary home in a cloud of vaporized rock. This ejected material would carry the unique chemical signature of its temporary home, becoming a new generation of interstellar dust, ready to one day seed another system. This chaotic bombardment was not mere destruction, however. It was a vital part of planetary evolution. These colossal impacts delivered immense amounts of energy and material. They may have delivered the volatile compounds, including water, that our world so desperately needed, transported on icy planetesimals from beyond the frost line. They also likely delivered the building blocks for life itself, complex organic molecules that had formed in the cold dark of the molecular cloud and survived the journey. The very event that could erase a world also had the potential to enrich it. So how did our solar system emerge from this period of chaos to find the stable, clockwork harmony we see today? Not every grain of stardust finds a permanent home. While most were swept up in the grand construction of planets, a precious few escaped that fate entirely. They became cosmic fugitives, preserved in a state of suspended animation for over 4.5 billion years. Their hiding places are the frozen archives of our solar system, the asteroids and comets that never grew large enough to become worlds. Locked within these ancient, icy bodies, the original dust from the solar nebula remains untouched, a pristine sample of the raw materials from which everything else was built. This is not just old rock, it is a direct bridge to a time before our sun ignited. Scientists call these particles presolar grains, and they are the closest thing we have to a physical time machine. Each microscopic speck is a refugee from a different star, carrying within its atomic structure the unique signature of its birthplace. To find them, researchers look to messengers that have fallen to Earth. Micrometeorites, tiny particles collected from the upper atmosphere, often contain these ancient grains. More recently, missions like Japan's Hayabusa2 spacecraft have performed a feat of celestial archaeology, traveling to a carbon-rich asteroid named Ryugu, touching its surface and bringing precious grams of material back to our laboratories. Inside those samples, scientists discovered presolar grains older than our solar system itself. As astrophysicist Don Brownlee once said of such particles, they are literally stardust. The proof is in the isotopes, the slightly different forms of elements like carbon, oxygen, and silicon. The ratios of these isotopes are like a star's fingerprint, forged under the specific temperature and pressure conditions inside that dying star. By analyzing a single grain under powerful microscopes, researchers can read this fingerprint. They can determine if it came from a red giant star's gentle outflow, or from the violent ejecta of a supernova, or even from a more exotic type of star. Each grain is therefore a messenger, a tiny scroll of data inscribed not with words but with atoms, recounting a chapter of galactic history that no telescope could ever directly observe. Through them, we hold in our hands not just the building blocks of our world, but actual artifacts from other suns, other places, other times. This silent testimony from the dawn of creation begs a final, deeply personal question. If we are all made from this ancient, interstellar material, what does that truly mean for our place in the cosmos? The final, chaotic bombardment did more than just reshape our world. It delivered its most precious cargo. With the planets now largely formed, the solar system was still littered with the construction debris, countless leftover planetesimals that had escaped accretion. These ancient bodies found stable parking orbits in two primary reservoirs. Closer in, between Mars and Jupiter, the asteroid belt holds rocky and metallic remnants from the inner solar system's early days. Far beyond the orbit of Neptune, in the deep freeze of interstellar space, trillions of icy bodies make up the vast spherical Oort cloud, a frozen archive of the solar system's outermost raw materials. These are not merely inert rocks and ice balls. They are the solar system's original packing crates, and within them, perfectly preserved, lies the pristine cosmic dust and organic chemistry from the nebula's dawn. For billions of years, they orbited in quiet stability until a gravitational nudge changed everything. The immense gravity of a giant planet like Jupiter can act as a cosmic slingshot. A passing star's gentle tug can perturb the distant Oort cloud. These subtle influences can send one of these primordial time capsules hurtling inward on a new, fateful trajectory. An icy comet warmed by the sun begins to vaporize, sprouting a magnificent tail of gas and dust that is, in essence, a direct stream of ancient nebula material being sprayed into space. A dark, carbon-rich asteroid, knocked into a crossing orbit, becomes a silent projectile carrying a payload of complex carbon molecules. During the late heavy bombardment, the young Earth was in the direct line of fire from this celestial delivery service. Each impact was a transfer of ownership. When a comet composed largely of water ice and frozen gases struck our planet, it did not just explode, it vaporized, releasing its water into the nascent atmosphere, where it would eventually condense and fall as rain, filling the first basins. Carbonaceous asteroids, often called carbon chondrites, are some of the most primitive materials we can study. They are not just rock, they are more like cosmic fruitcakes, packed with organic compounds, amino acids, and even microscopic diamonds that formed around other stars. The violent impact of such an object would have scattered these essential ingredients across the globe, seeding the barren rock with the very building blocks of biology. This means the water in your glass and the carbon in your cells may have arrived via separate deliveries, one by icy comet and the other by rocky asteroid, in a bombardment that shaped our world's destiny. The journey of cosmic dust, therefore, does not end with the formation of a planet. It finds its ultimate purpose in the quiet chemistry that follows the chaos, suggesting that life itself may be a legacy written in stardust and delivered by ancient celestial messengers. The story of cosmic dust is not ours alone. We now have the profound ability to watch it unfold in real time, not in our past but in the nurseries of distant suns. Far beyond our solar system, orbiting young stars in vibrant stellar neighborhoods like the Orion Nebula swirl immense, glowing disks of gas and dust. These are not artists' impressions, they are direct observations captured by telescopes like the Hubble and the James Webb Space Telescope. We are witnessing the very same processes that built our planets occurring right now, hundreds of light years away. How do we peer into these distant construction sites? The key is infrared light. The tiny dust grains, warmed by the light of their newborn star, glow with a heat signature our instruments can detect. But the story is told in the shadows and the gaps. A dark, clear lane circling a star within its bright disk is a powerful clue, a path likely swept clean by the gravitational pull of an unseen, growing planet. Elongated shadows arcing across the disk's surface hint at the presence of vast, tilted rings of material, shaped by hidden gravitational architects. Sometimes we see magnificent spiral arms like the pattern in a whirlpool, stirred not by water, but by the gravitational hand of a massive planet carving its path. Each observation is a snapshot, a single frame from a billion-year-long movie. One disk shows a smooth, continuous haze of dust, a system still in its earliest, chaotic stages. Another reveals a complex series of sharp, dark rings and bright bands, a mature system where planets have already formed and neatly organized the remaining debris. By comparing these alien disks at different ages, we can test our models of planetary birth. We see that the fundamental sequence holds true everywhere. Dust grains stick, they clump, they clear gaps, they build worlds. This universal blueprint confirms a humbling and magnificent truth. The journey from a supernova's ashes to a planet's foundation is not a unique accident of our history. It is the standard operating procedure of a universe rich with the potential for new worlds and perhaps new stories. The universe is not a one-way street, but a grand celestial roundabout. While we have followed the incredible journey of dust from stars to planets, that is only half the story. For every grain locked into a world, another finds a way back into the cosmic flow, ensuring the cycle of creation continues. This is the dust cycle, the universe's ultimate recycling program, where the end of one story becomes the raw material for the next. Even now, as you listen, this process is happening all around us. Our own solar system is not a sealed vault. The constant, gentle pressure of sunlight, known as radiation pressure, acts like a cosmic breeze, slowly pushing the smallest dust particles out of the inner system. The solar wind, a stream of charged particles flowing from the sun, scours the surfaces of airless bodies like the moon and asteroids, knocking individual atoms and molecules loose to drift away. More dramatically, when asteroids collide in the belt, they do not just create craters, they generate immense clouds of fine powder and rubble, a significant portion of which is ejected entirely, becoming a new population of free-floating interstellar dust. This is a slow, steady leak of material back into the galactic reservoir, but the most profound recycling occurs on a far grander scale, tied to the ultimate fate of a star itself. Consider our own sun. Billions of years from now, having shone steadily for eons, it will begin to run out of the hydrogen fuel in its core. In response, it will swell into a magnificent but doomed red giant. Its outer layers will expand outward with serene, unstoppable force, slowly engulfing the inner solar system. Mercury will be the first to vanish, then Venus. Our own planet Earth will face this expanding wall of plasma. The oceans will boil away, the crust will melt, and the very rock of our world will be vaporized, returned to a state of elemental gas. Every mountain, every ocean, every fragment of that ancient cosmic dust locked within our planet for 4.5 billion years will be dissolved back into the star's atmosphere. It is a poetic and humbling closure. The material that was once expelled from a star, that journeyed across light years, that clumped and collided to form a world that nurtured life, is called home. But this is not an end, it is a transformation. In the red giant's final acts, those outer layers, now enriched with the digested remains of planets, will be gently blown away in a powerful stellar wind. This creates a new planetary nebula, a glowing cloud of gas and dust that carries within it a complex history. The iron from Earth's core, the silicon from its rocks, the oxygen from its water, all are now mixed with the star's own nuclear ashes, like ingredients stirred into a new batch of cosmic batter. This nebula will drift for millennia, eventually mingling with the interstellar medium. There, under the gentle pull of gravity, it will coalesce into a new molecular cloud. Within that cloud, the cycle begins anew. The dust grains will form again around new seeds carrying the legacy of countless previous generations. They will collapse into a new star surrounded by a new disk, giving rise to new planets. Those new worlds will be built in part from the atoms of our own. This means the story of cosmic dust has no true beginning or end. It is an eternal loop of dispersal and gathering, of construction and dissolution. The iron in your blood was forged in a star that died before our sun was born, and one day it will help form a planet around a star that has not yet ignited. You are not just made of stardust, you are a temporary custodian of atoms on an endless journey through time and space. This gentle rain from the heavens is not a metaphor. Every single day, our planet sweeps up somewhere between 100 and 300 tons of cosmic dust. This is not the dramatic fireball of a meteor shower, but a constant, silent precipitation of the tiniest particles, most smaller than a grain of sand. As Earth travels on its yearly orbit around the Sun, it plows through clouds of debris left behind by comets and the collisions of asteroids, gathering this ancient material like a ship collecting mist on its bow. These micrometeorites drift down through the layers of our atmosphere, taking months or even years to settle. A perpetual, invisible snowfall of stardust onto every continent and ocean. While it may seem insignificant against the vast scale of our world, this cosmic drizzle represents a continuous, physical link between our terrestrial environment and the dynamic solar system around us. But what if this connection is more than just symbolic? Some researchers are exploring a fascinating possibility that this ever-present influx of space dust might play a subtle, yet real, role in shaping Earth's climate. The idea hinges on two potential mechanisms. First, the dust itself, suspended high in the stratosphere, could scatter a tiny fraction of incoming sunlight back into space, creating a very slight cooling effect. Second, and perhaps more intriguingly, these particles can act as condensation nuclei. In the cold, clean upper atmosphere, water vapor needs a surface to freeze or condense upon. A floating speck of cosmic dust, rich in minerals, provides the perfect platform. By seeding the formation of high, thin cirrus clouds, this dust could potentially influence how much heat is trapped or reflected. Now, it is crucial to understand that this proposed effect is incredibly small, far outweighed by the dominant forces of greenhouse gases and solar cycles. Yet the theory gains a compelling twist when we consider the grander motion of our solar system. Our Sun, with all its planets in tow, does not travel a perfectly smooth path through the galaxy. It oscillates up and down through the plane of the Milky Way, completing a cycle every few tens of millions of years. During this long cosmic journey, we might periodically pass through denser clouds of interstellar gas and dust. If the flux of incoming particles were to increase significantly during such a passage, could the climatic nudge become more noticeable? Some scientists look to the geological record, searching for correlations between past climate shifts and potential timings of these galactic encounters. Whether or not this specific hypothesis holds, it underscores a profound and beautiful truth. Our planet is not a sealed terrarium floating in a sterile void. We are an open system bathed in a gentle wind of atomic heritage. The air you breathe, the ground you walk on, is continually being dusted with the same primordial stuff that once formed the planets. This ongoing connection reminds us that Earth's story is forever intertwined with the cosmos, a dialogue written in the silent fall of microscopic grains from the depths of space. The universe's most extreme physics is being recreated inside rooms on our own planet. To truly understand how cosmic dust forms in the violent hearts of dying stars, scientists have built machines that can mimic those unthinkable conditions. They cannot travel to a supernova, but they can bring a supernova's essence into the laboratory. The goal is deceptively simple: to take the raw elements we know exist in space, subject them to stellar levels of energy, and watch what happens as they cool. The tools for this are anything but ordinary. Researchers use immense laser systems capable of delivering pulses of light so intense and so brief they can flash heat a target to millions of degrees in an instant. In other experiments, specialized furnaces create controlled environments of searing heat and specific gas mixtures, simulating the expanding, cooling layers of a red giant's atmosphere. They start with pristine materials like silicon carbide, graphite, or pure metals, the suspected building blocks of stardust. With a precise zap from a laser or within the heart of the furnace, these solids are not just melted, they are completely vaporized into a hot, dense plasma, a cloud of dissociated atoms mimicking the raw state of matter in a stellar outflow. Then comes the critical phase, the careful, controlled cooling. Just as in space, the temperature is allowed to drop, and in that cooling, magic happens. The free atoms, no longer energized enough to stay apart, begin to seek each other out. They collide, they stick, they form tiny clusters. Under the watchful eyes of electron microscopes and mass spectrometers, the scientists observe as these clusters grow, particle by particle, into nanoparticles. They can adjust the cooling rate, the pressure, or the gas composition, and each change produces a different kind of grain, some smooth and spherical, others with intricate fractal structures. This is how they decode the universe's recipes, by comparing the lab-made grains to the actual Presolar grains found in meteorites. They can perform a kind of cosmic forensics. If a dust grain from the Murchison meteorite has a particular shape and chemical signature, researchers can run experiments to see what combination of temperature, pressure, and cooling time produces an identical grain. It is a process of reverse engineering, working backwards from the artifact to understand the event that created it. These experiments do more than just confirm what happens. They reveal possibilities no telescope could see. They show how certain organic molecules might form on the surfaces of these grains in the dark of a molecular cloud, or how the magnetic properties of tiny iron nanoparticles could influence the collapse of a star-forming region. This hands-on approach transforms cosmic dust from a distant mystery into a tangible branch of materials science and chemistry. It bridges the immense gap between the faint light of a nebula caught by a telescope and the physical reality of a solid object you could, in principle, hold between your fingers. The laboratory becomes a portal, allowing us to witness the first moments of a grain's life, and in doing so, to run the universe's oldest recipe right here on Earth. Under the most powerful microscopes, cosmic dust reveals itself as a gallery of microscopic sculptures. These are not the simple, uniform spheres one might expect from a cosmic assembly line. Instead, they are intricate artifacts, each shape a frozen record of a specific moment in their epic journey. When scientists capture particles from the tails of comets or collect interplanetary dust in the stratosphere, they find an astonishing diversity of forms. Some grains resemble delicate, fractal snowflakes, not of ice but of mineral. These are the fluffy aggregates, collections of thousands of even smaller particles stuck together in a fragile, open web. Their structure is so porous that they are mostly empty space, with densities so low they could float on air. This confirms the gentle, sticky collisions that first built planetesimals in the cold outer disk, a process preserved in microscopic amber. Other grains tell a story of intense heat and orderly formation. They appear as perfect geometric crystals, tiny jewels of minerals like olivine or pyroxene. These crystals could only have formed in a hot, molten environment, perhaps near the newborn sun itself, before being flung outward to the cold regions where comets formed. Their presence in a comet's icy heart is a clue to the tremendous mixing that occurred in the young solar system, where material from the fiery inner forge was transported to the frozen outer archives. But perhaps the most enigmatic structures of all are known as GEMS, an acronym for glass with embedded metal and sulfides. Found within the most primitive interplanetary dust particles, these grains are a chaotic mosaic. Imagine a tiny, dark blob of glass, and embedded within it are even tinier nuggets of pure iron-nickel metal and specks of sulfide minerals, all jumbled together without a hint of order. This bizarre, heterogeneous structure is their key feature. It suggests they were not formed in a single, calm event. Instead, they are likely cosmic collages, assembled from components that experienced wildly different histories. The glassy matrix might have formed in the scorching outflow of a red giant star, while the metal nuggets could be condensates from the violent ejecta of a supernova. These separate materials then drifted through the interstellar medium, eventually colliding and sticking together in the cold, dark molecular cloud that predated our Sun. A single GEMS grain, smaller than the width of a human hair, can thus contain a layered biography of multiple stellar deaths and interstellar journeys, all preserved in microscopic detail. Their very disorder is their message, a testament to the universe's messy, creative, and deeply interconnected methods of construction. The beauty of the cosmos is painted with dust. While this material builds the foundations of worlds, its most immediate and breathtaking role is as the universe's artist, sculpting light itself into the magnificent structures we call nebulae. Far from being dark, empty voids, these vast clouds are illuminated canvases where dust interacts with starlight in a delicate dance of physics and color. The result is some of the most iconic and beloved sights in all of astronomy, visible proof that the universe values not just function, but form. Take the shimmering blue haze that surrounds the Pleiades star cluster, often called the Seven Sisters. This is a classic reflection nebula. Here, the light from brilliant, hot, young stars does not pass through the cloud unimpeded. Instead, it strikes countless microscopic dust grains. These tiny particles are exceptionally efficient at scattering shorter wavelengths of light, which we see as blue in all directions, much like the way our own sky scatters sunlight. The dust does not create new light. It simply takes the star's intense white radiance and diffuses it into a soft, ethereal blue glow, revealing the cloud's contours. It is a cosmic spotlight with dust as both the scrim and the lens. In other regions, dust performs a more active role. Within the vibrant heart of the Orion Nebula, ultraviolet radiation from newborn, searingly hot stars bombards the surrounding cloud. This intense energy strips electrons from atoms of gas, causing them to glow in characteristic colors, primarily a deep red from hydrogen. But the dust is there too, woven throughout the glowing gas. It absorbs some of this fierce ultraviolet light, warms up, and then re-emits the energy as a gentle, pervasive infrared warmth and a softer, visible glow. This dust acts as a moderator and a highlight, adding depth and texture to the nebula's fiery appearance. Without these countless grains, the brilliant structures of the Orion Nebula would be largely invisible to our eyes, the ultraviolet light passing through unseen. This humble material, then, is essential to our very perception of cosmic beauty. It transforms invisible energies into a visible palette, sculpting raw starlight into the pillars, loops, and curtains that fill telescope images. It reminds us that the universe's grandeur is not a separate phenomenon from its physical processes, but a direct and glorious consequence of them. The same dust that will one day clump into a planet is, for now, painting a masterpiece on a scale of light years. The search for life beyond Earth is a search for chemistry in the right place at the right time and with the right ingredients. For decades, the guiding principle has been the Goldilocks zone, that narrow orbital band around a star where temperatures allow liquid water to exist on a planet's surface. But water alone is not enough. The story of cosmic dust reveals a deeper, more nuanced truth that the very material which delivers the seeds of life can also become an obstacle to its survival. To find a truly habitable world, we must look at the entire dust life cycle of its solar system. In a system's youth, a robust protoplanetary disk is essential. It is the delivery network that transports water, ice, and complex organic molecules from the cold outer regions to the rocky planets forming in the warmer inner zone. A system with a sparse, anemic disk might produce rocky worlds, but they could be bone dry and devoid of the chemical richness needed for biology to begin. The initial abundance of dust sets the stage, yet as a system matures, the script flips. What was once a constructive force must quiet down. Imagine a hypothetical Earth-like planet, orbiting a Sun-like star, positioned perfectly in the habitable zone. Now imagine that this planet's orbit is perpetually swept by a dense cloud of debris, the leftover grit from planetary formation that never settled into stable rings or was cleared away. A constant, sandblasting rain of fine particles would not just pockmark the surface, it could actively erode a protective atmosphere over geological time. Even more critically, frequent impacts by larger bodies, driven by gravitational instability from leftover planetesimals, could deliver catastrophic blows, sterilizing the surface repeatedly and preventing life from gaining any lasting foothold. A quiet, orderly system where planets have successfully cleared their orbital neighborhoods appears to be a prerequisite for long-term stability, but dust's influence does not end with bombardment. It continues in the planet's own sky. The presence and composition of atmospheric dust can dramatically alter a world's climate. On a planet like Mars, global dust storms can raise temperatures across the entire planet by trapping heat. For an exoplanet, such dust, whether from volcanic activity, surface winds, or occasional impacts, would complicate our observations. It could mask the subtle atmospheric signatures, or biosignatures, we are trying to detect, like the telltale combinations of oxygen and methane. Alternatively, certain types of high-altitude dust could reflect just enough sunlight to help stabilize a climate, acting as a natural thermostat. This means that to assess a distant world's true potential, we must learn to read the dust both in its past and in its present. We need to understand the history of its solar system's construction and the current state of its skies. The search for life is no longer just about finding a planet at the right distance from its star. It is about finding a world with the right story, a narrative written in the accumulation, and then the peaceful settling of the very dust from which it was born. Observing these microscopic travelers across the emptiness of space is a task that pushes the very limits of human ingenuity. How do you study something smaller than a grain of sand when it is light years away? The answer lies not in a single, perfect instrument, but in a symphony of technologies, each listening for a different note in the story of dust. To see the universe's hidden architecture, we must look with more than just our eyes. This requires a fleet of specialized observatories, each tuned to a different part of the electromagnetic spectrum, working in concert to decode the faint signals from these tiny particles. The most powerful tool for mapping dust is infrared light. Think of a dusty room on a sunny day. You can see the motes floating in the air where the sunbeam shines through, but the room itself is hazy. Now, if you could see in the infrared, the dust itself would glow with its own warmth, revealing its shape and density directly. This is precisely what telescopes like the James Webb Space Telescope do. They are exquisitely sensitive to heat. By detecting the faint thermal glow of warm dust grains, these instruments can peer straight through the obscuring veils of dusty nebulae to witness the newborn stars blazing within. They reveal the intricate structures of protoplanetary disks, showing us the swirling construction sites of alien solar systems in vivid detail. For a completely different perspective, we turn to radio telescopes. These vast, silent dishes listen not for light, but for the faint whispers of molecules. In the cold depths of molecular clouds, simple atoms like carbon and oxygen stick to the surfaces of dust grains and undergo chemical reactions. The resulting molecules, like carbon monoxide or complex organic compounds, emit unique radio signatures as they spin and vibrate. By mapping these spectral lines, radio astronomers can trace the otherwise invisible presence of the dust grains that serve as the universe's essential chemical laboratories. They are listening to the chemistry of life's ingredients as it happens in the dark. But to truly understand the physical nature of this material, we must reach out and touch it. This is the realm of daring spacecraft missions. NASA's Stardust mission performed an act of celestial interception, flying through the tail of a comet called Whirlpool. It extended a collector filled with a substance called aerogel, an incredibly light and porous material that acted like cosmic flypaper. As cometary dust particles slammed into it at high speed, they were gently captured, preserved in pristine condition. When the capsule returned to Earth, scientists held in their hands actual pieces of a comet, grains that had been untouched since the dawn of our solar system. Each method provides a distinct piece of the cosmic puzzle. Infrared observations show us where the dust is and how it is shaped. Radio data tells us what chemistry is occurring on its surface. And sample return missions let us analyze its atomic composition and physical texture under a microscope. Only by combining these views, from the macro scale of a nebula down to the nanoscale of a single grain, can we trace the complete, incredible journey of stardust, from its fiery birth to its gentle arrival in our laboratories. The relentless churn of geology beneath our feet holds a secret mirror to the galaxy above. Our planet has its own eternal loop, the rock cycle, a process so vast and slow it shapes continents over eons. A mountain of granite, born from cooled magma deep within the Earth, is slowly cracked by ice and worn by rain. Its fragments are carried by rivers to the sea, settling into layers of sand and silt. Over millennia, those layers are buried, compressed, and cemented into solid sandstone. Deeper burial might bake and twist that stone into a new form, a metamorphic rock like quartzite. And if tectonic forces drag it down into the planet's searing mantle, it melts once more, ready to rise again as new igneous rock. This cycle has no true beginning or end, only transformation. The atoms are never destroyed, they are simply rearranged, moving from one state to another in a slow, planetary dance. This familiar process is a perfect human-scale analogy for the journey of cosmic dust, but on a stage that spans the galaxy and operates over billions of years. In this grand cosmic cycle, stars are the volcanoes. They are the furnaces where raw elements are forged, the equivalent of Earth's molten mantle producing new igneous rock. The supernova's explosive outflow or the red giant's gentle wind is the eruption, spraying this freshly minted material into the galactic environment. Then comes the weathering. The harsh environment of interstellar space acts like an eternal, gentle sandblaster. Radiation and cosmic rays slowly alter the surfaces of dust grains, and collisions in molecular clouds chip and reshape them. This is the cosmic equivalent of wind and rain breaking down a mountain. Next is sedimentation and lithification. The dust grains, along with gas, settle into the vast, flat disk around a young star. Through gentle sticking and gravitational collapse, they are compressed and bound together, forming planetesimals and then planets. This is precisely like layers of sediment on an ocean floor being buried and turned into solid stone. The planet itself becomes the archive, the sedimentary rock layer of the galaxy. Finally, the cycle completes with the return to the heat. For some dust locked deep within a planet like Earth, the journey ends only when the star itself dies. As our sun becomes a red giant, it will reclaim its children, vaporizing the inner worlds and pulling their material back into its atmosphere. That material, now enriched with planetary history, will be blown out again in a new nebula. This is the ultimate metamorphism and melting, the closing of the loop. The key insight is one of profound continuity. Nothing in the universe is ever truly lost or created from nothing in these processes. Every atom is a traveler on an infinite journey, wearing different forms like costumes. The calcium in your teeth was once part of a star's fiery breath, then a mineral grain in a distant nebula, then a component of an asteroid, before being delivered to a young Earth and incorporated into living structures. The rock cycle teaches us that the ground we stand on is never permanent, merely in a temporary state. The cosmic dust cycle reveals that we ourselves are in a temporary state, a fleeting arrangement of ancient atoms on loan from the universe. This perspective shifts our understanding from one of isolated events to one of an unbroken, elegant flow, a symphony of transformation playing on every scale, from the pebble in a stream to the spiral arm of a galaxy. This undeniable physical truth carries a weight far beyond the laboratory. The journey from stellar forge to human form is more than a sequence of events. It is a narrative of origin that redefines our place in the cosmos. Astronomer Carl Sagan famously expressed this with poetic clarity, noting that the nitrogen in our DNA, the calcium in our teeth, the iron in our blood were all made in the interiors of collapsing stars. We are, in the most literal sense, star stuff. This is not a metaphor. It is a chemical fact written into the very fabric of our being. Every breath you take pulls in oxygen atoms that were fused in a star that died before our sun was born. The strength in your muscles relies on iron nuclei forged in the final moments of a supernova, a cataclysm that scattered those atoms across light years of space. The carbon that forms the backbone of every organic molecule in your body was created in the heart of a red giant and carried here on icy comets. You are a walking, talking archive of galactic history. This realization bridges the immense gap between the cold, vast universe and the intimate reality of our own existence. It tells us we are not separate from the cosmos, looking out at it from a distant, fragile oasis. We are an expression of it, a localized concentration of its most creative processes. The universe, in its patient cycles of destruction and creation, has fashioned a way to look back at itself, to wonder about its own nature. This connection transforms our perspective from one of isolation to one of profound kinship. The same forces that sculpt nebulae and spin galaxies also assembled the components of life. This shared lineage suggests that the story we have traced, the journey of cosmic dust, is not merely something that happened to our planet. It is the story of how the cosmos built the raw materials for consciousness itself. The philosophical dimension is this: we are the universe becoming aware of its own beauty and complexity. The stardust within us is not a relic of a dead past, but a vibrant, ongoing testament to a creative, interconnected reality. It invites a sense of awe that is both humbling and empowering, reminding us that in exploring the cosmos, we are ultimately exploring our own deepest ancestry. The universe's first moments were a canvas of almost perfect simplicity. In the primordial glow following the Big Bang, only the lightest elements existed, a sparse soup of hydrogen, helium, and a whisper of lithium. There were no planets, no rocks, not even a single speck of solid material. It was a transparent, elemental universe, lacking the microscopic grit that would one day build worlds and blot out starlight. For cosmic dust to exist, the universe first had to forge something heavier. This required a new kind of alchemist, the very first generation of stars. Astronomers call them population 3 stars, and they were unlike anything that came after. Born from the pure, unpolluted gas of the early cosmos, with no heavy elements to help them cool and fragment, these stars grew to be monstrous. They were behemoths, hundreds of times more massive than our sun, burning ferociously bright and living fast, explosive lives. Their fate was sealed from birth. After only a few million years, a mere blink in cosmic time, they exhausted their fuel and met a cataclysmic end. In their violent supernova deaths, the furnaces of creation roared to life for the first time. The intense heat and pressure within these explosions fused the primordial hydrogen and helium into a new periodic table: carbon, oxygen, silicon, iron. And as those expanding shockwaves plowed into the cold surrounding gas, something unprecedented happened. For the first time in history, atoms heavier than lithium found each other and stuck. The first solid particles in all of existence condensed out of the fire. This was the universe's initial pollution event, the moment the pristine gas was seeded with the heavy elements and the dust necessary for everything to come. Detecting this primordial dust, however, is one of the greatest observational challenges in all of astronomy. We are looking for a microscopic haze at the edge of time itself. Our most powerful telescopes must act as time machines, capturing light that has traveled for over 13 billion years. The clues come from the most distant and luminous objects we can find: quasars, the brilliant cores of ancient galaxies powered by voracious black holes. As the light from these cosmic beacons journeys across the universe to reach us, it passes through intervening clouds of gas and dust. By analyzing the specific fingerprints or absorption lines in the quasar's spectrum, astronomers can discern what that light passed through. Astonishingly, the light from some of the most distant quasars shows subtle signs of having been reddened and absorbed by dust. The implication is staggering. It means that within just a few 100 million years after the Big Bang, well before our own galaxy had fully taken shape, the first generation of massive stars had already lived, died, and enriched their surroundings with solid matter. Dust formation began with breathtaking speed. This rapid transition marked a fundamental shift in the character of the cosmos. The early universe was transformed from a simple, transparent sea of gas into a more complex, textured, and opaque one. Light now had something to scatter against, to hide behind, and to warm. The stage was no longer empty. The first props, microscopic though they were, had been placed, setting in motion the cosmic cycle of construction that would eventually lead to galaxies, stars like our Sun, and planets like Earth. The same ancient dust that built our world now presents a stark duality to our future among the stars. For the next generation of explorers venturing beyond Earth, this material will be both a silent adversary and a potential ally. The danger lies in its speed and ubiquity. Across the solar system, countless micrometeoroids, often just grains of dust or tiny pebbles, travel at velocities exceeding tens of thousands of miles per hour. At those speeds, even a speck the size of a grain of sand carries the kinetic punch of a bullet. It can pit windows, degrade solar panels, and, in a worst-case scenario, puncture a spacecraft's pressure hull or damage a critical system. These are not rare events, they are a constant whispering rain that every vessel must endure. The challenge intensifies on planetary surfaces. The Apollo astronauts discovered this firsthand on the Moon. The lunar soil, or regolith, is not like Earth's dirt. It is a blanket of fine, glassy, and jagged dust created by billions of years of meteorite impacts that pulverized and fused the rock. This abrasive powder clung to everything, clogging the seals of their spacesuits, jamming equipment joints, and even causing a form of lunar hay fever, irritating their eyes and lungs. For a long-term lunar base or a journey to Mars where similar dust exists, managing this invasive grime becomes an engineering priority for both machine and human health. Yet within this problem lies a profound opportunity. This very dust, this troublesome regolith, is essentially a raw ore deposited on our cosmic doorstep. It is rich in oxygen, locked chemically inside minerals like silicates and iron oxides. With the right technology, we could bake or process this soil to liberate that oxygen, providing breathable air and a key component of rocket fuel. The dust also contains metals like iron, aluminum, and titanium, all potential feedstocks for three-dimensional printing tools, constructing habitats, or building radiation shields. Suddenly, the hazardous environment becomes a potential quarry. This shifts the mission profile from one of carrying everything from Earth at immense cost to one of living off the land, a concept called in situ resource utilization. The success of this approach hinges on a deep, granular understanding of cosmic dust, its exact composition, its mechanical behavior, and how it reacts in different environments. Designing a dust-tolerant spacesuit hinge or an efficient oxygen extraction plant requires us to be planetary geologists and chemists, turning a historical obstacle into the foundational resource for a sustained human presence in the cosmos. The dust that once built our home planet may now hold the key to building our first permanent homes away from it. Long before telescopes revealed its physical truth, humanity felt the pull of stardust in its soul. This profound connection is woven into the very fabric of our stories, a recurring dream across civilizations that we are made of something celestial. Ancient myths from cultures around the world speak of gods molding humans from clay mixed with starlight, or of life itself being breathed into being from cosmic breath. These were not scientific statements but intuitive truths, a poetic understanding that we belong to something greater than the earth beneath our feet. The idea that we carry a spark of the heavens within us provided a narrative of origin that linked the human experience directly to the majestic, mysterious night sky. This cultural thread did not vanish with the dawn of modern science, it evolved. Poets and songwriters have long used stardust as a metaphor for magic, memory, and the intangible essence of love and loss. A popular song from the last century speaks of being made of stardust and golden, capturing that timeless feeling of wonder. In film and literature, characters often find their destiny written in the stars or discover that a magical substance from fallen meteors holds the key to life itself. These stories resonate because they touch on a universal longing, a desire to see our own lives as part of an epic, beautiful, and meaningful cosmic story. This cultural backdrop makes the scientific revelation not a cold dismantling of myth, but a breathtaking validation of it, the laboratory proof that we are literally assembled from ancient stellar material gives tangible, physical form to that ancient intuition. It transforms metaphor into magnificent fact. Contemporary artists now work directly with this powerful intersection. Creators like Luke Jerram craft exquisite glass sculptures of viruses based on scientific models or create artworks that contemplate lunar material. Their work lives in the space between data and wonder, using the aesthetics of science to evoke the same awe that the original myths did. By exploring this cultural dimension, we see that the journey of cosmic dust is more than a chain of physical events. It is a narrative that fulfills a deep, enduring human need. We have always sought to understand where we come from, and in tracing the path of stardust, science has given us the most authentic origin story ever told, one that roots our existence in the grand, creative fires of the universe itself. This synthesis of knowledge and wonder does not diminish the mystery, it deepens it, inviting us to see our art, our stories, and our very selves as continuous with the cosmos. But for all we have learned, the cosmic ledger does not quite balance. A profound discrepancy lingers in our observations, a gap between what our theories predict and what our telescopes actually see. This is known as the missing dust problem, and it challenges our most fundamental models of how galaxies grow. The math seems straightforward. We know how much dust a typical supernova should produce based on its elemental output and the physics of condensation. We can count the rate of these stellar explosions in the early universe. When we multiply these figures, the result is a prediction of immense dust abundance, a universe that should have been murky with the soot of countless dying stars. Yet when we point our most powerful instruments at the most distant, and therefore youngest galaxies, the numbers rarely add up. The dust is simply not there in the quantities we expect. It is as if a cosmic thief has been quietly siphoning off the building blocks of future worlds. So where did it all go? One compelling possibility is that we have overestimated dust's durability. The environment inside a young, vibrant galaxy is far from peaceful. It is a maelstrom of intense radiation from newborn stars and frequent shockwaves rippling through the gas from nearby supernova. A delicate, newly formed dust grain drifting through such a chaotic neighborhood might not last long. A single powerful shockwave could shatter it through collisions, or intense ultraviolet radiation could blast it apart, sublimating the solid particles back into a diffuse gas. In this scenario, dust is being constantly created and then almost immediately destroyed, a frantic cycle that leaves little time for it to accumulate to the levels our simpler models predict. Another intriguing explanation points not to destruction but to a change in form. Perhaps the dust is not missing at all but hiding. If conditions are right, dust grains could clump together with astonishing efficiency, aggregating not into planetesimals but into vast, cold clouds or even dim, starless objects. These structures would be so cold they emit almost no infrared light, the primary signal we use to hunt for warm dust. They would be cosmic ghosts, invisible to our current search methods, locking away the universe's raw material in a form we cannot yet see. Solving this puzzle is not just an academic exercise, it is essential for accurately telling the story of cosmic evolution. The amount of dust in a galaxy controls how quickly stars can form, how light escapes, and how planets eventually assemble. If we are wrong about the dust, we are wrong about the very life cycle of matter itself. This missing dust problem is a humbling reminder that for every answer we uncover, the universe presents a deeper, more subtle question, inviting us to look again, to think differently, and to refine our understanding of the grand, dusty tapestry of creation. This hidden language of light is a whisper we have learned to translate. Spectroscopy is the art of listening to that whisper, of reading the unique fingerprints that cosmic dust leaves on the light that passes through it. When astronomers point a telescope at a star, they are not just collecting a point of brightness. They are capturing a story, written in the full spectrum of its light, from the deepest reds to the invisible infrared. A spectrograph acts like an ultimate prism, splitting that light into an exquisitely detailed rainbow, revealing dark lines and bright bands that are the signatures of specific atoms and molecules. Dust writes its chapter in this spectral book in two distinct ways. First, it absorbs. Imagine holding a colored filter up to a light. If a dust grain contains silicate minerals similar to the sand on a beach, it will preferentially absorb light at a very specific infrared wavelength around 10 micrometers. This creates a dark dip, an absorption feature in the star's spectrum at that exact location. A grain rich in carbon will create a different dip. It is as if each type of material has left a unique thumbprint in the starlight, a shadow that reveals its identity from across the vastness of space. But dust does not only take away light, it also gives it back. Those same grains, warmed by the starlight they absorb, re-radiate the energy as heat. This creates a second signature, a gentle, continuous glow in the infrared part of the spectrum. The color and shape of this infrared hum tell a detailed story. A warmer glow indicates dust closer to the star, while a cooler, redder emission points to dust in the frigid outer reaches of a system. The precise slope of this emission can even hint at the size and structure of the grains, whether they are tiny and uniform or large and fluffy. By reading these spectral fingerprints from distant nebulae, the dusty disks around young stars, or even the combined light of entire galaxies, astronomers can perform a kind of remote forensics. They can map the distribution of silicate versus carbon dust across a spiral arm, estimate the temperature of debris rings around other stars, and infer the presence of icy mantles on grains in cold molecular clouds, all without ever leaving Earth. This silent dialogue between light and matter transforms every point of light in the night sky into a complex message, waiting for us to decipher its dusty secrets. A single speck of cosmic dust is almost inconceivably small. Picture the width of a single human hair. Now, imagine slicing that hair into 1,000 equal slices along its width. One of those slices is roughly the size of a typical interstellar dust grain, about 0.1 micrometers across. This is the realm of the truly microscopic, where the rules of quantum physics begin to whisper, and the surface area of a particle becomes more significant than its volume. This is our protagonist, a near-nothingness of mineral and carbon, embarking on the grandest of voyages. Its journey begins with unimaginable velocity. Forged in a supernova, it is catapulted into the void by the shock wave of that stellar death, initially traveling at thousands of kilometers per second. That is a speed that could carry it from Earth to the Moon in under 2 minutes. Yet, this blistering pace does not last in the diffuse interstellar medium. It is like a bullet fired into honey, quickly slowed by countless gentle collisions with solitary atoms and the drag of magnetic fields. For the next phase of its existence, it drifts. It is no longer a projectile, but a wanderer moving at a relative crawl through a sea of nothingness. This stage of the journey is defined not by speed, but by patience, lasting for millions of years as the grain slowly circles the galactic center. The scale of its environment during this drift is equally staggering. It traverses the interstellar medium, but its ultimate destination is a molecular cloud. These are not small things. A single such cloud can span dozens of light years. To comprehend that, consider a light year is about 9.5 trillion kilometers. The grain must cross this immense, foggy cathedral, a journey that makes a human lifetime seem less than a single heartbeat in comparison. Within that cloud, the process of accumulation begins, a gravitational gathering that operates on a scale of hundreds of thousands of years. Then the final act of assembly accelerates. Drawn into the whirlpool of a protoplanetary disk, our dust grain becomes part of a construction project of planetary proportions. Over perhaps 100 million years, through countless gentle collisions and mergers, it is incorporated into ever larger bodies. The microscopic speck becomes part of a pebble, then a boulder, then a mountain-sized planetesimal, and finally, it is locked deep within the structure of a world thousands of kilometers in diameter. The planet Earth, for instance, is roughly 12,700 kilometers across. The journey from a 0.1 micrometer particle to a component of that colossal sphere represents an increase in scale of over 100 billion times. This transformation is not magic. It is the inevitable consequence of gravity and simple sticking forces, given enough time and material. It is a demonstration that the universe possesses a profound creative patience, an ability to build landscapes of breathtaking complexity and scale from the most humble of beginnings. The mountain you see on the horizon, the bedrock beneath your city, the very ground you stand upon, was once a diffuse, invisible haze of microscopic minerals, each on a lonely voyage that only together could create something whole. The pristine dust from a comet's heart, safely sealed within its aerogel tomb, represents more than a scientific triumph. It is a profound responsibility. As our technological reach extends, allowing us to pluck grains from asteroids and capture particles from the solar wind, we are no longer passive observers. We have become active collectors of cosmic heritage, and with that power comes a complex set of ethical questions. These microscopic samples are not mere rocks, they are irreplaceable pages from the solar system's first chapter. Once a sample is altered by Earth's atmosphere or consumed in an experiment, that unique record is changed forever. So how do we, as a species, decide who gets to study these precious fragments of our shared past? The legal framework is surprisingly sparse. The The foundational Outer Space Treaty, established during the space race, clearly states that celestial bodies themselves cannot be claimed by any nation. This principle prevents a new era of cosmic colonialism, but the treaty is silent on the finer details. If a nation or a private company brings back a kilogram of asteroid regolith, who owns those specific particles? Are they the property of the entity that retrieved them, or do they belong to all of humanity as part of our common heritage? The scientific community has largely answered this not through law, but through careful, self-imposed practice. Consider the lunar samples brought back by the Apollo astronauts. They are curated with near-sacred care at facilities like NASA at Johnson Space Center, housed in ultra-clean rooms filled with pure nitrogen to prevent any terrestrial contamination. Access to these materials is granted not to the highest bidder, but to researchers from around the world whose proposed experiments pass rigorous peer review. The goal is preservation for future generations. Scientists today analyze Apollo moon rocks with instruments far more advanced than those available in the 1970s, uncovering new secrets from the same slices of stone. This long-term stewardship model ensures that the knowledge encoded in cosmic dust is treated as a global scientific commons, a library where the books are so rare they can never be checked out, only read under careful supervision. It transforms the act of retrieval from one of possession into one of custodianship. We are not taking these samples for ourselves, we are bringing them home for all of humanity, and for the scientists of the future who will ask questions we have not yet even learned to pose. The silent census of our galaxy is about to begin. Later this decade, a new eye will open on a mountaintop in Chile, the Vera C. Rubin Observatory. Its mission is not to stare at single objects, but to watch the entire accessible sky night after night for 10 years. This relentless survey will capture the faintest flickers of change, and among them, a crucial signal, the gentle, temporary dimming of distant stars. This dimming is often the shadow of a dust cloud, drifting between us and the star like a cosmic veil. By mapping millions of these subtle events, the observatory will construct a dynamic, three-dimensional atlas of dust distribution throughout the Milky Way. We will no longer see dust as a static haze, but as a moving, evolving component of our galactic ecosystem, tracing its flows and concentrations with unprecedented clarity. To understand the chemistry within those clouds, we must listen. On the high plains of South Africa and Australia, construction is underway for the Square Kilometre Array, a radio telescope of staggering sensitivity. Its thousands of dishes will act as one giant ear tuned to the faint whispers of molecules. Where the Rubin Observatory sees the dust shadow, the SK will hear the conversation happening on its surface. It will map the emission lines of carbon monoxide, water, and complex organic molecules across vast stretches of interstellar space, revealing exactly how dust grains catalyze chemistry in different environments, from the turbulent spiral arms to the quiet outskirts of galaxies. This will tell us not just where the dust is, but what it is doing. Our reach will extend beyond observation to direct contact. Future robotic explorers destined for the outer solar system, perhaps to the ice giants Uranus or Neptune, will likely carry a new generation of dust analyzers. These instruments could capture and instantly vaporize particles encountered during the long voyage, reading their elemental and isotopic composition in real time, telling us the specific history of dust in that remote region. Even more tantalizing are proposed sample return missions to the moons of Mars, Phobos, and Deimos. These small, dark bodies are widely believed to be captured asteroids, time capsules from the early solar system. Bringing back material from their surfaces could deliver to our labs a pristine collection of dust that has been orbiting Mars for billions of years, untouched by planetary geology or an atmosphere, offering a pure sample of the ancient building blocks delivered to the inner planets. Together, these tools represent a fundamental shift in our quest. We are moving from sketching the broad outlines of dust's epic journey to writing its detailed biography, chapter by chapter, in different galactic neighborhoods. We will witness its life cycle from birth to dispersal, not as a theoretical model, but as a measurable process, varying from the crowded galactic center to the serene halo. This is the promise of the next era, to transform our understanding of cosmic dust from a component of the scenery into a dynamic character in the ongoing story of the universe, whose every interaction we can now hope to witness and comprehend. The universe operates not as a collection of isolated events, but as a single, breathing organism. This is the profound lesson written in the journey of dust. The life cycle of a single grain connects stellar furnaces to planetary oceans in a chain of cause and effect so complete it rewrites how we see everything. A supernova's death rattle seeds a cloud with heavy elements. That enriched cloud collapses into a new generation of stars, but now the presence of dust changes the rules. Dust shields the cloud's interior, allowing it to fragment into smaller, longer-lived stars like our Sun. It is a self-regulating loop where the products of star death directly control the birth of future stars. This feedback mechanism is the hidden rhythm of galactic evolution. A galaxy with vigorous star formation becomes dustier. That dust then cools the interstellar medium, making it easier for even more stars to form, leading to brilliant bursts of creation. Yet, if star formation runs too hot, the resulting supernova can blast that same dust away, shutting down the process until things settle. The dust content is both a product and a director of the galaxy's story, a dynamic participant in its own destiny. This interconnectedness scales seamlessly from the galactic to the profoundly personal. The iron in the hemoglobin carrying oxygen through your veins was forged in a star that died before our solar system existed. That iron atom was part of the dust that helped our molecular cloud cool and collapse. It was swept into the protoplanetary disk, incorporated into an asteroid, and later delivered to Earth during the late heavy bombardment, becoming part of the planet's core. Billions of years later, geological processes and biological evolution brought it to the surface where it was taken up by plants, consumed, and integrated into the very molecules that keep you alive. Your existence is a point of convergence for threads that span the galaxy and stretch back to the beginning of time. The calcium in your bones, the phosphorus in your DNA, the oxygen in your lungs, each has a lineage that winds through supernova, icy comets, and ancient impacts. This is not poetry, it is a chemical and physical fact. You are a nexus where cosmic history becomes conscious. Seeing the cosmos through this lens transforms our understanding. It challenges the old, compartmentalized view of astronomy, where stellar astrophysicists, planetary scientists, and astrobiologists worked on separate puzzles. Now we understand they are all working on different pieces of the same grand image. The study of a distant protoplanetary disk informs our models of Earth's formation. The analysis of a presolar grain in a meteorite provides data on nucleosynthesis in ancient stars that no telescope can ever observe. The detection of complex organic molecules on a comet speaks to the universal chemistry that might seed life elsewhere. Every discovery in one field illuminates the others because they are all linked by the common thread of material flow. The universe is a closed system of matter and energy, endlessly rearranging itself. In tracing the path of a single speck of dust, we trace the circulatory system of the cosmos, seeing how its grandest structures and its most intimate details are woven from the same fabric, telling one continuous, magnificent story. This timeline is not measured in centuries, but in galactic revolutions. To grasp the full weight of a speck of cosmic dust is to stretch your mind across a span of time so vast it defies everyday intuition. Our entire solar system, with its stately planets and warming sun, is a relative newcomer, coalescing roughly 4.6 billion years ago from that swirling nebula of gas and grit. But the most ancient ingredients within that cloud were far older. They were the legacy of stars that had lived and died billions of years before our sun even ignited. A presolar grain, one of those microscopic refugees from another star, can be over 5 billion years old. It is a senior citizen of the cosmos, older than the very star that gives us light and warmth. Consider the journey of such a grain. It formed in the cooling atmosphere of a red giant or the expanding shockwave of a supernova during an era when our galaxy looked profoundly different. It drifted through the silent interstellar dark for eons. Then it was gathered into the local cloud that would become our solar system. It witnessed, as a passive participant, the furious whirl of the protoplanetary disk, the violent collisions of planetary embryos, and the great bombardment that shaped our young world. All the while, life on Earth was beginning its own slow, patient experiment, evolving from single-celled organisms in ancient seas to the creatures that would one day walk on land and gaze at the stars. Through the rise and fall of dinosaurs, the shifting of continents, and the entire span of human history, that grain rested, locked inside an asteroid or a comet, a silent witness to the unfolding story of a planet it helped build. Now it rests under the lens of a microscope in a clean room laboratory. A scientist, using tools of incredible precision, probes its atomic structure to read its history. This moment is a profound intersection of timelines. The grain's narrative, spanning over 5 billion years, meets our human story of curiosity, a story that has developed the technology to retrieve and understand such a thing. To hold, even metaphorically, such an object is to hold a piece of deep time itself. It is a physical bridge between the galaxy's distant past and our present moment of awakening comprehension. This connection collapses the immensity of cosmic history into something tangible, transforming abstract billions of years into a solid artifact you could, in principle, balance on a fingertip. It asks us to consider our own brief moment not as an isolated event, but as a recent sentence in a story that began with the first stars. The cold, dark void of a molecular cloud is not a chemical desert, but a silent workshop. Here, in the profound chill just a few degrees above absolute zero, the universe begins its most delicate work, assembling complexity from simplicity. This intricate process does not happen in empty space. It requires a solid stage, a microscopic platform where lonely atoms can find each other and hold on long enough to bond. That stage is the humble surface of a cosmic dust grain. In the diffuse interstellar medium, a free-floating hydrogen atom and a free-floating oxygen atom might collide, but they are far more likely to bounce apart than to form a stable water molecule. Their meeting is too fleeting, like two strangers passing in a vast dark field. But introduce a dust grain and everything changes. This tiny speck of silicate or carbon provides an anchor. When a wandering atom strikes its surface, it sticks, if only for a moment. It becomes absorbed, held in place by weak molecular forces. Now it waits. Soon, another atom drifts in and sticks nearby. Trapped together on this microscopic island, they are no longer lonely travelers. They are neighbors, and they can react. The dust grain's surface acts as a catalyst, lowering the energy needed for a chemical reaction to occur. Hydrogen atoms link with oxygen to form water, right there on the grain. Carbon monoxide molecules can be transformed into more complex organic compounds. This is not a rare event. It is a constant, quiet industry happening on trillions upon trillions of microscopic surfaces throughout the cloud. The products of this surface chemistry do not simply float away. In the deep cold, they freeze, building up layer by layer into an icy mantle that encases the original dust grain like a frosty shell. This mantle is not just decoration, it is a protective vault. Within its frozen matrix, the newly formed molecules are sheltered from the harsh ultraviolet radiation that would otherwise tear them apart. The ice acts as a cosmic deep freeze, allowing molecular complexity to accumulate safely over millions of years. Simple molecules like water and carbon monoxide become the foundations for more elaborate structures. Through further reactions on the grain's surface or within the ice itself, molecules like methanol, formaldehyde, and even amino acids can form. These are the very building blocks of biology, the precursors to proteins and genetic material being manufactured in the darkness of interstellar space. Then a new star ignites nearby. Its warmth begins to seep into the cloud, a gentle thaw after an eon of deep freeze. As temperatures rise, the icy mantles surrounding the dust grains begin to sublimate, turning directly from solid ice into gas. In a process astronomers call ice desorption, the vaults are opened. The complex organic molecules held within are released, enriching the surrounding gas of what will become the protoplanetary disk. This event is a cosmic seeding. The disk that forms around the young star is no longer just a swirl of simple gases and mineral dust. It is now infused with a rich soup of pre-made organic compounds, a chemical inheritance delivered directly from the cold nursery of the molecular cloud. When planetesimals and comets form in the outer, icy regions of this disk, they inherit this complex chemistry. They become frozen arcs carrying within them water, methanol, and amino acids from the interstellar medium. Later, during the violent era of planetary bombardment, these icy bodies will crash into young worlds like Earth, delivering their precious cargo. The water in our oceans and the chemical seeds for life on our planet may have begun as a faint frost on a speck of dust in a cloud light years away. This transforms our understanding of cosmic dust from a passive building material into an active, essential participant in the story of life itself. It was not merely the brick that built the house, but the workshop that forged the key to the door. Building a digital universe from a speck of dust is a challenge of staggering complexity. The galactic dust cycle is not a single event, but a symphony of processes, each with its own tempo and scale, and trying to compose that symphony inside a computer is one of the most ambitious tasks in modern astrophysics. The problem is one of scope. A single simulation must somehow bridge the microscopic and the galactic. It must account for the nuclear physics inside a dying star, where elements are forged at temperatures of billions of degrees, and then track those atoms as they are blasted into space by a supernova shockwave that expands over light years. That same model must then slow down time to simulate the quiet, patient drift of a dust grain through the cold, near vacuum of the interstellar medium for millions of years. It needs to model the delicate surface chemistry on that grain, where icy mantles form and complex molecules assemble, and then, in a sudden shift, simulate the violent gravitational collapse of an entire molecular cloud, where that grain is swept into a whirling protoplanetary disk. Finally, it must follow the grain through countless collisions, from gentle sticking to planet-smashing impacts, until it is locked into a new world. Each of these stages operates on a completely different set of physical laws, timescales, and densities. It is like trying to write a single computer program that can accurately simulate the physics of a nuclear explosion, the growth of a snowflake, and the erosion of a mountain range. The computational power required is mind-boggling. Researchers use the world's most powerful supercomputers, running for months at a time, to track the fates of millions or even billions of virtual particles. But even with this immense power, compromises are unavoidable. To make the problem tractable, scientists must make simplifying assumptions. They might treat a vast cloud of gas as a smooth fluid rather than a collection of individual atoms, or model the growth of dust grains using statistical averages instead of tracking every single collision. These approximations are necessary, but they mean that every simulation is a carefully crafted approximation of reality, not a perfect mirror. The true test comes when we hold these digital universes up to the light of real observation. Astronomers compare the output of their models to the actual multi-wavelength data we collect from telescopes. Does the simulation produce the same amount of infrared glow from warm dust that we see in a spiral galaxy? Does it predict the correct ratio of carbon-rich dust to silicate dust in a supernova remnant? If the model's galaxy looks too dusty or not dusty enough compared to the real one, it is a clue that something is missing or simplified too much. Perhaps the model destroys dust in supernova shockwaves too efficiently, or maybe it underestimates how quickly grains can grow in dense clouds. Each discrepancy is a gift, a puzzle that forces theorists to refine their equations and programmers to write more elegant code. This back and forth between the digital and the observed is an iterative dance of discovery. With each cycle, the models become more sophisticated, incorporating new physics and finer details. We are slowly, painstakingly, building a virtual laboratory where we can run experiments on the life cycle of the cosmos itself. In this digital universe, we can rewind time to watch the formation of our own solar system, or fast forward to see the fate of another. We can ask what-if questions that the real universe takes billions of years to answer. What if the first stars were less massive? Would that change the amount of dust in early galaxies? What if a galaxy experiences a major collision? How is its dust redistributed? These simulations are more than just complex video games. They are proving grounds for our understanding, allowing us to witness the entire epic biography of a dust grain, from its fiery birth in a star to its quiet rest in a planet, all within the memory of a machine. The shimmering blue haze of the Pleiades and the dark lanes of the Orion Nebula are not just distant wonders, they are invitations. For scientists and educators, the story of cosmic dust is a powerful bridge, a way to translate the abstract equations of astrophysics into a narrative that resonates on a deeply human level. This material offers a unique key for public outreach because its journey is our own origin story, written in atoms we can all understand. In planetariums around the world, this science becomes a breathtaking sensory experience. Visitors are no longer passive observers, but are immersed inside a swirling protoplanetary disk, surrounded by a cosmic carousel of glittering dust that slowly coalesces into planets before their eyes. These visualizations, based on real telescope data, transform complex models into an intuitive, awe-inspiring spectacle. It makes the invisible process of planetary birth not just visible but visceral. Meanwhile, in the quiet halls of natural history museums, a different kind of beauty is on display. Under powerful electron microscopes, dust grains from meteorites reveal themselves as microscopic sculptures. A Presolar grain becomes a jagged, crystalline jewel. A fluffy aggregate looks like a delicate, fractal snowflake. These images are often displayed as works of abstract art, their forms and textures captivating viewers before the accompanying label even explains their cosmic significance. This aesthetic hook draws people in, creating a moment of wonder that makes them want to learn the incredible story behind the image. In classrooms, the concept of stardust is a revolutionary teaching tool. A chemistry lesson on the periodic table transforms when students learn that every element heavier than lithium was forged in a star. The iron in their blood, the calcium in their bones, becomes a direct link to a supernova that exploded billions of years ago. An Earth science unit on the rock cycle gains galactic context when compared to the grand cosmic dust cycle, showing our planet as part of a much larger, dynamic system. This approach makes science personal. It moves beyond memorizing facts to fostering a profound sense of connection. When a person internalizes that they are literally made of material from ancient stars, their relationship with the night sky changes. It is no longer a distant, impersonal void. It is home. This sense of cosmic belonging is the ultimate goal of this outreach. By focusing on this tangible, material link, scientists and educators can cut through the complexity and speak directly to a universal human curiosity about our place in the grand scheme. This work is vital. It transforms cosmic dust from a niche subject of astrophysics into a shared story of heritage and wonder. It inspires not by demanding advanced degrees, but by offering a simple, profound truth that everyone can carry with them. A truth that might just spark the imagination of the next great explorer or thinker who looks up at the stars and feels for the first time a personal connection to the light. Our understanding of cosmic dust is a map with blank spaces still waiting to be filled. For all the connections we have traced, from supernova to our own biology, fundamental mysteries remain stubbornly unresolved, each one a frontier where our knowledge meets the edge of the unknown. One of the most persistent puzzles is the exact mechanism that allows dust to leap the meter-sized barrier in a protoplanetary disk. We know that particles must grow from microscopic flecks to mountain-sized planetesimals, but the middle stage is perilous. At around the size of a boulder, drag from the swirling gas should cause these objects to spiral inward rapidly, doomed to fall into the star before they can grow any larger. Our models suggest clever loopholes like gravitational instability or the sticky properties of icy mantles, but which of these processes dominates in a real disk? Is it a combination, or is there a universal shortcut we have not yet imagined? Observing this critical phase directly is incredibly difficult, as these meter-sized objects are too small and dark to see around distant stars, leaving us to infer the answer from the planets they ultimately become. In the deep freeze of molecular clouds, another question lingers. We know dust grains act as cosmic chemistry sets, but what is the full inventory of complex molecules they can create? Telescopes have detected the spectral fingerprints of simple organics like methanol and formaldehyde in these clouds, and amino acids have been found in meteorites. This suggests the building blocks are there, but are more elaborate structures, the direct precursors to proteins or genetic material, also being assembled on these icy grains. The challenge is that these larger molecules are harder to detect from afar, their spectral signatures fainter and more tangled. We are, in a sense, trying to read a recipe book by looking at the scattered ingredients through a frosted window. Until we can bring back more pristine samples from comets or directly probe these clouds with more sensitive instruments, the true chemical richness of this probiotic soup remains a tantalizing mystery. Even the lifespan of a dust grain is uncertain. We understand how dust is born in stellar outflows, but how efficiently is it destroyed? The interstellar medium is a dangerous place, filled with shockwaves from supernova and blistering ultraviolet radiation from hot young stars. A grain might be shattered in a collision or vaporized by a radiation blast, but how often does this happen? The rates of destruction are crucial for balancing the cosmic dust budget. If dust is destroyed too quickly, our models cannot explain the amounts we see in mature galaxies. This missing dust problem hints that either our destruction estimates are too high, or dust is much better at hiding in cold, dark clumps than we thought. Unraveling this requires a galactic census, tracking not just where dust is, but where it isn't and why. Perhaps the most profound open question reaches back to the dawn of time. Can we ever definitively detect the signature of the very first dust grains, forged by the universe's inaugural generation of stars? These population 3 stars were giants that lived fast and died young, and their explosive death should have seeded the early cosmos with the first solid particles. We see hints of dust in the spectra of incredibly distant quasars, light that has traveled for over 13 billion years. But is that dust from those first stars or from a slightly later generation? The signal is faint and ambiguous. Finding a confirmed relic of that primordial era would be like discovering the first brick ever made. giving us direct insight into the initial conditions of cosmic construction. It remains a holy grail for observers, pushing our telescopes to their absolute limits. These unanswered questions are not failures of science, they are its engine. Each mystery about cosmic dust represents a boundary of our current understanding, a line on the map marked "Here be dragons." They remind us that the journey we have traced is not a completed story, but a living narrative. Every new telescope, every sample return mission, every advanced simulation is an attempt to answer these open challenges. The pursuit pulls us forward, driving a cycle of curiosity, observation, and revelation that peels back the universe's deepest secrets layer by layer. In acknowledging what we do not know, we chart the course for all the discoveries yet to come. The same forces that sculpt nebulae are at work in our clean rooms and factories. The universe has been performing nanoscale engineering for billions of years, and now, by studying cosmic dust, we are learning to replicate its methods for our own technology. Consider the birth of a dust grain in the cooling wind of a red giant star. Atoms vaporized in the stellar furnace are ejected into space where they rapidly cool. In that sudden chill, they lose energy, begin to stick together, and condense into solid nanoparticles. This process of vaporization followed by condensation is not unique to stars. It is the fundamental principle behind a suite of human manufacturing techniques. In facilities that produce advanced semiconductors or the thin, conductive films for solar panels, engineers use precisely controlled versions of this same physics. They vaporize a target material in a vacuum chamber, then allow it to condense onto a silicon wafer, building circuits layer by atomic layer. The universe, in its stellar outflows, runs a scaled-up, chaotic version of this same laboratory process. By analyzing the size, composition, and structure of stardust, materials scientists gain insights into how to better control nucleation and growth here on Earth, potentially leading to more efficient solar cells or novel electronic components. But the lessons go beyond creation to architecture. Cosmic dust rarely exists as isolated, solid spheres. More often, especially after gentle collisions in molecular clouds, it forms intricate fractal aggregates. These are not dense rocks but delicate, open frameworks like microscopic snowflakes made of mineral. Their structure gives them remarkable properties, combining incredible lightness with surprising strength, because stresses are distributed across a vast network of tiny connections. This is a masterclass in efficient design from nature, or rather from the cosmos. Researchers in materials science and nanotechnology look to these forms for inspiration. Could we engineer synthetic materials that mimic this fluffy, fractal geometry? The potential applications are profound, from ultra-lightweight yet super-strong structural composites for aerospace to highly porous scaffolds for advanced filtration systems or battery electrodes, where maximizing surface area is key. Perhaps the most direct technological transfer comes from the dust grain's role as a catalyst. In the cold dark of a molecular cloud, the surface of a silicate or carbon grain is where hydrogen and oxygen meet to form water, where simple carbon molecules begin linking into more complex chains. The grain's surface provides a platform that lowers the energy required for these reactions, guiding chemistry towards specific outcomes. This is the very definition of a catalyst, and it is a process industry depends upon. From refining petroleum to manufacturing fertilizers, we use solid catalysts to make reactions faster, cleaner, and more efficient. By studying the exact atomic arrangements and mineral compositions that make cosmic dust such an effective chemical facilitator in space, chemists can dream up new catalyst designs for use on Earth. We might discover a surface structure that converts carbon dioxide into fuel with minimal energy, or one that creates vital pharmaceuticals with less waste. This is the beautiful circular payoff of fundamental science. A researcher peering through a telescope at a distant nebula or analyzing a meteorite grain under a microscope is driven by pure curiosity about our origins. They are tracing a story written in atoms, yet the knowledge they uncover about vapor deposition, fractal strength, and surface catalysis does not stay locked in an astronomy journal. It flows into engineering textbooks and industrial patents. It demonstrates that the drive to understand the cosmos is not separate from the drive to improve our world. They are two facets of the same human endeavor. The universe has been running experiments in material synthesis and chemical engineering since the first stars died, and we are only now beginning to read its laboratory notebooks. Could the most advanced civilizations in the galaxy be hiding in plain sight, written into the fabric of the cosmos itself? The search for extraterrestrial intelligence has long focused on listening for deliberate signals, radio waves or laser pulses beamed across the void. But what if the clearest evidence is not a message, but a byproduct, an unintentional signature etched into the very dust that fills interstellar space? This is a speculative yet fascinating avenue of thought, one that reframes cosmic dust not just as a natural material, but as a potential canvas for technological activity. The logic stems from a simple principle: any civilization that reaches a certain scale of energy use must, by the laws of physics, leave a thermodynamic footprint. A star emits a colossal amount of light. If an advanced society were to build a vast array of structures, often imagined as a Dyson swarm, to capture that starlight for its own needs, the star's visible light would be partially obscured. But energy cannot be created or destroyed, only transformed. That captured stellar energy would eventually be irradiated as waste heat, a diffuse glow in the mid-infrared spectrum. To a distant observer, this signature would look remarkably similar to a shell of unusually warm dust encircling the star. Our telescopes are already adept at detecting the infrared warmth of natural dust clouds around young stars. An anomalous, persistent infrared glow around an older, sun-like star, with no accompanying natural explanation like a debris disk, would be a profound anomaly, a potential techno-signature written in heat. Beyond stellar engineering, consider planetary activity. An industrial civilization, even one not intending to broadcast its existence, would alter the chemistry of its home world's atmosphere. Combustion or advanced manufacturing could release complex synthetic molecules, rare isotopes, or unusual combinations of gases that would not occur in such concentrations naturally. These atmospheric pollutants would not simply float in isolation. They would interact with the planet's own dust, whether volcanic ash, wind-blown silt, or micrometeoritic debris. Unique chemical compounds could form on the surfaces of these grains, creating a layer of anthropogenic dust with a distinct spectral fingerprint. If a cataclysmic event or the slow erosion of time were to loft this dust into space, these chemically altered grains would become tiny messengers, carrying the faint, scrambled signature of a civilization's activity out into the galaxy. While this idea is not a primary method for SETI, and extraordinary natural explanations must always be ruled out first, its value is profound. It forces us to think in terms of indirect evidence and unintended consequences. It asks us to consider how intelligence, through its sheer scale and duration, becomes an environmental force, altering the planetary and even stellar systems it inhabits in ways that might be detectable across the light years. In this view, cosmic dust becomes more than a historical record of stellar death and planetary birth. It becomes a potential registry of cosmic activity, a medium that might one day carry not just the story of how worlds are made, but the subtle, lingering trace that someone was there to make something of them. These threads of transformation, connectivity, persistence, ubiquity, and revelation are not separate strands, but a single, interwoven tapestry. They tell us that the universe operates as a unified system, where the fate of a single atom is inseparable from the destiny of a galaxy. Transformation is the fundamental law. A dust grain is never static. It begins as a vaporized element in a star's heart, condenses into a solid speck in the cold of space, gathers an icy mantle, clumps into a mountain, and is later buried in a planet's mantle, only to be potentially vaporized again when that star dies. Its journey is a constant dance between states of matter, between destruction and creation, proving that change is the only constant in the cosmos. This relentless transformation is powered by connectivity. The iron atom forged in a supernova does not exist in isolation. Its journey connects the violent death of one star to the gentle birth of another. It links the field of astronomy, which studies that stellar explosion, to the field of geology, which studies the iron ore in Earth's crust, and to the field of biology, which studies the hemoglobin in our blood. Dust is the physical hyperlink that makes these disciplines different chapters of the same story. It shows us that the universe is not a collection of isolated events, but a vast, intricate network of cause and effect. For this network to function, persistence is essential. It seems contradictory. How can something so microscopic and fragile survive the violence of a supernova shockwave, the harsh radiation of interstellar space, and the violent collisions of a young solar system? Yet it does, not through brute strength, but through adaptability and sheer numbers. Individual grains may be destroyed, but the material itself endures, cycling from one form to another across timescales that dwarf human history. This persistence ensures that nothing is truly lost, only repurposed, allowing the story to continue across billions of years. This leads to ubiquity. We find this material everywhere we look. It is in the dark bands cutting across the Milky Way, in the glowing nebulae where stars are born, in the tails of comets that visit our inner solar system, and in the gentle haze that dims the light of the most distant galaxies. It is also in the soil of your garden and the air you breathe. This universal presence is a powerful clue. It tells us that the processes we see in our own cosmic backyard are not unique. They are the standard operating procedures of a universe rich with the same fundamental ingredients. All of this culminates in revelation. It is a profound truth of science that by studying the smallest, most humble components, we often uncover the largest truth. A single Presolar grain, smaller than a bacterium, can tell us about the interior composition of a star that died before our sun was born. The faint infrared glow of dust in a distant galaxy reveals its star formation history. By focusing on these tiny messengers, we decode the grand narrative of cosmic evolution itself. Together, these themes paint a portrait of a universe that is dynamic, creative, and deeply interconnected. They suggest a cosmos where elegance emerges from simplicity, where the grandest structures are built from the most modest beginnings, and where our own existence is a natural, though wondrous, outcome of these universal processes. The story of dust is therefore not just a tale of astronomy, but a framework for understanding our place within an ongoing, magnificent creation. Sunlight reveals the universe in your living room. Watch a beam of light cut through a window, and you will see countless tiny specks drifting in a slow, weightless dance. Most are flakes of skin, fibers from fabric, or grains of soil from our own planet. But among them, hidden in plain sight, are rare visitors from space. Every day, our atmosphere captures a fine rain of interplanetary dust, particles so small they settle gently to the ground without burning up. These micrometeorites land on your roof, your car, even your windowsill. While finding one requires a careful search with a magnet and a microscope, their presence transforms that sunbeam from a simple household phenomenon into a cosmic light show, a daily reminder that our world is not isolated. Look at your own hand. The gold in a wedding band or the platinum in a watch carries an even more extraordinary pedigree. these heavy elements are not forged in the common fires of a supernova. They are born in the most violent and rare events in the cosmos, the collisions of neutron stars. When these incredibly dense stellar corpses spiral together and merge, they spray out a cloud of material rich in gold, platinum, and other precious metals. This stellar debris condenses into dust that eventually finds its way into new solar systems. The precious metal you wear is therefore a relic of a cataclysm so powerful it warps the fabric of space-time, now resting quietly against your skin. This connection is woven into the very substance of life, the carbon that forms the backbone of every molecule in your body. From the sugars in your breakfast to the DNA in your cells, was fused in the heart of a star. The nitrogen in your muscles and the oxygen you breathe with each lungful of air share that same stellar origin. When you eat an apple or drink a glass of water, you are ingesting atoms that once swirled in the glowing envelope of a red giant or were scattered by a supernova blast. Your body is not just borrowing this material, it is constantly recycling it, exchanging these ancient atoms with the environment in a cycle that literally ties your biology to the life cycles of stars. This realization collapses the immense distance between the cosmic and the personal. The story of astronomy often feels scaled to the incomprehensible, measured in light years and billions of years. But by recognizing the stardust in the sunbeam, in your jewelry, and in your next meal, that vast narrative suddenly finds a human scale. It becomes intimate. You are not a passive observer of the cosmos looking out at a distant spectacle. You are an active participant. With every breath, you draw the legacy of stars into your body. With every movement, you stir atoms with histories older than our planet. The journey of cosmic dust does not end in a distant nebula or a far-off planet. It culminates here, in the quiet miracle of a conscious universe reflecting upon itself. You are where the story becomes aware. The story of a single dust grain is, in its essence, a story of us. We too are formed from a past we can scarcely comprehend, assembled from genetic and cultural legacies that stretch back into deep time. Just as a speck of stardust carries the elemental fingerprint of a long-dead star, we carry within us the quiet imprints of ancestors, of languages, of discoveries, and of stories passed down through generations. We are born into a vast and often turbulent environment, a world of swirling social currents, historical forces, and personal challenges that shape our path, much like the interstellar medium guides a wandering particle. Our lives are defined by transformation. We are not static beings. We learn, we grow, we suffer losses, we experience profound joy, and with each experience we are fundamentally altered. The child is not the adult, the student is not the master, and through every chapter we shed old ways of thinking and adopt new perspectives, a constant state of becoming that mirrors the dust grain's journey from gas to solid to part of a world. And crucially, we find our meaning in connection. A solitary human life is a profound story, but it is in coming together that we build something larger than ourselves. Families, friendships, communities, and civilizations are the human equivalent of accretion. We stick together through gentle bonds and sometimes forceful collisions, merging our energies, our ideas, and our labor to create structures of incredible complexity and resilience. A city, a library, a scientific discovery, a work of art, these are the monuments built by countless souls clumping together across time, creating something that endures beyond any single lifetime. Yet the metaphor also speaks to our transience. On the scale of cosmic time, a human life is breathtakingly brief, a flicker against the eons. The individual components of our physical selves, the atoms that form our bodies, are on loan. They were here long before us, assembled into countless other forms, and they will return to the Earth's great cycles when our time is done, to be taken up by other living things, by the air, by the soil. This is not an end, but a redistribution, a return to the system from which we came, This perspective could feel diminishing, but it does the opposite. It weaves our personal narrative into the grandest tapestry imaginable. To see yourself as part of this eternal cycle is to understand that your existence is not an accident, but an expression of the universe's most fundamental creative processes. Your capacity for love, for curiosity, for awe is the cosmos becoming conscious of itself. Your actions, however small they may seem, create ripples. A kind word, an idea shared, a problem solved, a child taught. These are the gentle gravitational nudges that can alter the orbits of other lives in ways you may never see. They are the legacy you contribute to the ongoing construction, the unique chemical signature you add to the collective whole. This cosmic metaphor, therefore, offers a profound sense of place. It fosters a humility that comes from knowing we are small, yet simultaneously grants a dignity that comes from knowing we are made of and participate in something magnificent. It encourages a deep connection, not only to each other but to the very planet and star system that gave us form. And above all, it invites a sustained and quiet awe, a recognition that to be alive and aware in this universe is to be a temporary custodian of stardust with the privilege of witnessing for a fleeting moment the beauty of the story itself. This narrative of dust is ultimately a story of unity. From the furious heart of a dying star to the quiet chemistry of a dark cloud, from the violent construction of a planet to the gentle pulse of life upon it, every stage is connected by an unbroken flow of matter. We have followed these microscopic travelers not as distant curiosities, but as the essential threads weaving together the cosmos. They are the catalysts that shield delicate molecules, the messengers carrying stellar histories, the time capsules preserving our deepest past, and the very fabric from which worlds and we are sculpted. This journey reveals a cosmos that is not a collection of isolated events, but a single, breathing entity in a state of perpetual transformation. The realization that we are woven from this ancient material changes everything. It reframes our existence from a chance occurrence on a lonely rock to a natural, even inevitable, chapter in the universe's grand biography. We are the cosmos becoming conscious, a way for the universe to know itself. The atoms in your hands right now, the ones that let you feel the weight of your phone or the texture of this page, have witnessed the birth and death of suns. They have drifted through light years of silent darkness and survived the chaos of planetary collisions, all to become part of you in this fleeting, precious moment of awareness. This knowledge is not meant to make us feel small, but to instill a profound sense of belonging. You are not a visitor to this universe, you are a vibrant expression of it. So carry this story with you. Let it color the way you see the night sky, not as a distant tapestry, but as a homeland. Let it deepen your curiosity about the intricate connections that bind atoms into molecules, planets into systems, and stardust into stories. As the astrophysicist Neil deGrasse Tyson reminds us, we are not figuratively but literally stardust. This is the most authentic origin story we have, a truth written in the elements of our being. If this journey through cosmic history resonated with you, we would love to hear your reflections in the comments below. For more explorations into the profound mysteries of space, subscribe to continue the adventure. And the next time you step outside, take a moment to look up. The light from those stars is a greeting from your distant cousins, and the air in your lungs is a testament to an epic journey that led against all cosmic odds.